Hello and welcome. Thank you for attending today's session, From Mainframe to Microservices, Vanguard's Move to the Cloud. My name is Ilya Epstein. I'm an Enterprise Solutions Architect with AWS. I'm joined by Barry Sheward, Chief Enterprise Architect from Vanguard. I had the privilege of working with Vanguard's team for the last 2 years on their cloud journey. Many of the customers that I work with have mainframe systems, and those mainframe systems have centralized data stores and monolithic applications. A lot of those customers want to move the mainframes to the cloud, so we're going to talk about some of the modernization approaches of how you could move mainframes to the cloud and how you could, what are some of the key considerations. Then Barry's going to do a deep dive into the Vanguard's cloud data architecture, and he's going to talk about the strangulation pattern that they're leveraging. And he's going to share a lot of the benefits and lessons learned, hopefully that you could take back to your organizations. So for most customers, a journey to the cloud is also a journey to microservices. Although there may not be a precise definition of what a microservice is, there are some very common characteristics. So for example, microservices typically have reusable modules that are build deployed independent. Microservices typically communicate with each other through an API interface. They're usually organized around the capabilities of that microservice or the business versus the specific technology stack. So what you often will see, instead of having teams that are UI-based or middleware-based or database, the microservices teams are organized around that specific microservice. So at Amazon, for example, we call that the two pizza teams. Microservices will typically own their domain logic, and they'll have decentralized governance and data stores. From a data store perspective, a lot of times each microservice will leverage the data store of its choice. So if NoSQL makes more sense, or if a relational database makes more sense for specific microservices, you will usually use the data store that actually makes sense. And then you're also going to start seeing a lot of decentralized data governance, right? So Barry's going to talk about concepts like bounded context, and he's going to talk about eventual consistencies. Those are some of the things that you see when customers move to microservices. Microservices are almost always deployed in an automated way, so this is where you're going to have continuous integration and hopefully continuous delivery. And they have to be designed for failure, right? So there is definitely a lot more stress that has to be put into testing your clients because microservices could fail, so you need to make sure that your application and your clients could respond to those failures. I think from a benefits going to microservices, I think it's pretty obvious. It removes the business logic and data logic from your applications. It helps customers eliminate the technical debt as they move to the cloud. And it helps you eliminate the monolithic bottlenecks, right? Because each microservices team could operate independently, could have their own deployment schedules, and there's just not a lot of dependencies across the teams. And what customers are trying to achieve is they're trying to improve the developer velocity. So this all sounds great, right? But how do you get there if you are running mainframes, if you have monolithic applications, centralized data stores, a single CI/CD pipeline, maybe 2-3 releases a year? So how do you get to the cloud? Unfortunately, there's still no announcement around just lifting and shifting a mainframe to the cloud. So what are some of the approaches? So the good news is that there are successful patterns out there. Over the last couple of years, we've seen some really great things from a lot has to do with our partners, and some of our customers have had great successes in these approaches. So for example, one approach could be a rehost approach. What a rehost approach does is it, for the most part, maintains your COBOL code. Nothing changes from that perspective. But what you will do is you will recompile that code on a permanent emulator that you will run on EC2. So you are tied to an emulator. You will also need some third-party tools to control things like printing and maybe access to storage. But there is a way to rehost that mainframe. And there's some third-party solutions that do that. Of course, some of the challenges with that type of approach that we'll talk about is that you may not be gaining the full value of the cloud. There are also multiple re-engineering options, and there are kind of different subcategories in that area, right? So one approach could be refactoring. We have some partners in the space which are providing tools that will actually do automatic code conversion, and they'll try to refactor it. So this is not a lift and shift. What they're actually doing is they're analyzing the application model of your mainframe, and then they're trying to create a similar application model leveraging AWS native services. So this could give you access to microservices. It could give you access to higher level AWS managed services. And in some cases, that code conversion could be done automatic. There are also options, of course, to manually rewrite your microservices your functionality into microservices over time. And then there's a whole bunch of different data-driven approaches as well. So, for example, migration of batch jobs, right? So where you could potentially be streaming data from your centralized data store, or you could be moving files, let's say your vSAM files, into S3, and then just implementing certain aspects like batch reporting. It could also be analytics capabilities, where you're taking that data, moving it to the cloud, and then performing your analytics in the cloud. Those are all aspects of re-engineering. Re-platform could be an option. This is really specifically if you're running your mainframe with Linux. I think about 75% of z/OS mainframes are actually leveraging some Linux. So if you have Linux and Java applications on your mainframe, you could potentially do some re-platform and run that on EC2. And then, of course, there's repurchase and retire, where some of the functionality will simply be sunset over time, either by SaaS solutions or new functionality that you develop. For most customers, it's a combination of all of these approaches, right? Some functionality will naturally be retired, some of it will be maybe re-hosted, and some of it could be re-platformed. There are a lot of considerations to think about, right? Things like risk and impact to your operations. But two of the factors that I also want to call out are cloud business value and the time it takes to do the migrations, right, or to do the modernization. So if we look, for example, at a rehost option, from an operational perspective, it's probably the least amount of risk. It also doesn't require your teams to retool as much. But when you're doing a rehost, you really are not taking the full value of the cloud, right? Because you're running in this emulator environment. You're not using microservices. You're not using some of the AWS managed services. You really are not getting a lot of value. But you could get to the migration pretty fast. And sometimes when customers have things like data center closures and they just simply need to get out and move to the cloud, they'll take that approach. With refactoring, automatic, let's say, code conversion, you'll definitely be running in native AWS services. So that allows you to then get more business value from the cloud. But of course, the timing could be a little bit more, for example, than rehost. And then, of course, rewriting, that's where you get the most value because you're doing things in the most cloud-native way possible, and you're making new decisions as you're rewriting the code. But of course, that's typically a multi-year journey. The good news is we do have professional services teams and partner teams that actually have expertise in each one of these areas, so we could definitely help in that space. But we also have customer successes in each one of these approaches. For today's session, we're primarily going to talk about re-engineering, and the focus is going to be on kind of data-driven re-engineering. And the approach that the Vanguard team is going to be taking is going to focus on, focusing on the data and then potentially rewriting some of the code into microservices. So Martin Fowler, I think every tech conference has Martin Fowler slide. He had a great observation. I think he's the first one that coined the term the strangler pattern. What he was doing is he was in an Australian rainforest, and he observed these fig trees that had these vines. What happens is I think a bird or a bat will put a seed on the upper branches of a tree, and it'll start putting vines all the way down to the soil. And over time, you have these hundreds and thousands of vines that go all the way down to the soil, and eventually they actually cover up the host tree entirely. And then on the soil level, they actually end up competing for the nourishment. And then eventually the host tree actually dies, and you basically have this new fig tree with a hollow inside. So he basically made an observation to take the same approach for monolithic to microservices migrations, where you're going to develop a new system around the edges, and over time, more and more functionality will move to that new system, and that original old system will eventually be strangled. So on a high level, what does that mean? So if you have your monolithic, let's say your mainframe with a centralized data store and a monolithic application, and you have your users accessing your application through a browser, over time, You'll develop a microservice. That microservice potentially could have its own data store, and then you'll put some type of a proxy tier in front of it or an API tier, and you'll redirect users to the new functionality. And then, of course, over time, you're going to build more and more of these services to a point where more of that functionality is using the new capabilities, and then the old system becomes strangled. The challenge we see sometimes is, depending on how that's implemented, it doesn't actually always lead to strangulation, because depending on how these new microservices are developed, you still could have a lot of dependencies, either on the actual monolithic code or potentially even just the monolithic centralized data store. So in practice, we are seeing sometimes customers have challenge where that actually is not achieved. So the approach that Barry's going to talk about is the approach of focusing on the data, right? Where you actually figure out a way how you could get the data to the cloud, and where your microservices are actually leveraging the native data stores in the cloud. And all of your writes you're not doing direct necessarily writes to the mainframe, you're leveraging things like eventual consistencies, bounded context, and where you don't have that tight dependencies to the on-prem data store or the monolithic code. And that's the approach that Barry's going to talk about. And with that, I want to introduce Barry, who's going to do a deeper dive in the Vanguard cloud data architecture. Thank you.
Thank you, Ilya. So I'm Barry Sheward, Chief Enterprise Architect at Vanguard. I work in a team called the Cloud Construction Team, which is part of the CTO office. We're going to be starting off talking a little bit about our legacy infrastructure, what we have at the moment, what we're hoping to move from, working to move from. Then we're going to start talking about some of the various architectures that we put together to help us move from mainframe to microservices. And then finally, we'll talk a little about lessons learned and things to bear in mind as you make the journey. First, just enough about Vanguard to give you some context of the organization. So I like to joke that we're a small investments company. We actually have over $4 trillion worth of assets under management. So it should tell you two basic things about the organization. Firstly, we're very conscious of security, particularly cybersecurity, making sure that we're well protected. And the second thing is we're very highly regulated. So organizations such as the SEC and FINRA will monitor us, make sure that our computation is both timely and accurate. If we don't get things timely and accurate, best case, we get irate customer phone calls that we need to spend money in order to process. Worst case, we get fined by organizations, the regulators, and we can sometimes end up on the front page of the Wall Street Journal, which is never a good thing if you're not there for the right reasons. We were founded 40 years ago. So basically, we've seen every generation of IT, from mainframe, mini computers, client server, service-oriented architecture, and microservices now, moving on towards cloud. Don't let my accent fool you. We are US-based, just outside of Philadelphia in Pennsylvania. And it occurred to me a couple of days ago that 40 years ago, our founder had the forethought to locate us almost exactly halfway between Wall Street in New York and the future home of Amazon's US East 1 data centers. We have a number of different lines of business. Two of our largest are the retail line of business, which allows individual investors to open accounts and trade mutual funds with us, and an institutional line of business, which obviously works with companies to provide 401ks, and for those of you not from the US, that's kind of like a pension, tax-deferred savings for use in retirement. Our institutional line of business is very focused on non-regulatory compliance such as SOC 2. So it's something that we can use to prove to our customers that we do things right in the IT space. And finally, we have no outside owners, so the returns on the investments we make provide better returns for our customers. And since our staff have 401ks with the company, we're actually incentivized to be as efficient as we possibly can and provide value to our investors. So our current IT environment obviously we have a whole bunch of data centers, a huge reserves to handle spikes in capacity and availability. And within those environments or data centers, we effectively have 3 types of operational system. We have the systems that our business uses in order to decide which mutual funds to buy, analytics data, those kinds of things. A lot of that is COTS software. We then have our system of record, which is our real old systems that keep track of who owns what within the system. And then we've got our system of engagement, which are the tools that we use to interact with our customers. Interestingly, 20 years ago, the system of record and the system of engagement were the same system, right? Customers would call up and the phone operators would be typing into mainframe consoles in order to make transactions happen. Nowadays, obviously, it's all web interfaces. Typically, our web interfaces, you can see here, custom web applications, 3-tier, large monolithic Java applications, very complex. Many of them now have internal caches, non-distributed, which means that all the sessions are stateless. Obviously, that impacts scalability. Our largest lines of business use DB2 on the mainframe for their data storage. And some of our other lines of business do use other databases as well. Our mainframe environment really is the crown jewels of Vanguard. We're not running Z-Linux. It's MVS-based. We have a build system for COBOL code and a version control system for it as well. And then DB2, which is the system that supports our system of engagement with our customers. There are at least 3,000 relational tables and 6,000 COBOL stored procedures in that system, which makes a trivial migration very difficult to achieve. We then have our record-keeping systems, part of our system of record, which is all based on vSAN files, CICS, KICS interfaces, and COBOL batch processes, and those typically run every night to perform all the necessary calculations. In order to provide the data from our system of record into our system of engagement, there's a huge number of integration processes that run, point-to-point integrations with multiple systems that move data from the record-keeping system into the database and vice versa. And typically that goes through MQ and COBOL batch processes. And then finally, people interact with our mainframe, a small amount through the CICS interfaces, slightly more through the MQ interfaces, but the largest interactions are through the DB2. So why is it we want to migrate? We're not doing 1 or even 2 migrations here. We're actually doing 3 separate migrations. The first is the migration to the public cloud. So we started to look at private cloud. We came to reInvent. We realized we can't possibly match Amazon. So let's look at using them. Gives us the ability to use infrastructure as code. We can spin up environments, as many as we need. We also get a lot of managed services, right? Why run our own message queuing systems, our own databases, when Amazon can run it for us, right? We're a financial company, not an IT company. And finally, if you're using on-prem systems, no matter how many you buy, there's still limits to the elasticity, right? And if you buy too many, they're sitting around. If you don't buy enough, you can't cope with the kind of spikes that you might experience. And those are the things that go away with public cloud. From the mainframe, moving off the mainframe perspective, firstly, with any proprietary system, if you can't get the same capability in the cloud provider of your choice, you're somewhat limited to, at best, a hybrid model. The cost of the mainframe, basically you're running an expensive vertically scaled system as opposed to being able to take advantage of cheaper horizontally scaled systems. We also have effectively our development staff divided into 2 parts. One part is the COBOL developers that work on the mainframe side. The other part is the Java developers that work on the system of engagement. We wanted a common programming model so that we didn't have to worry about the skills that are starting to be more difficult to find in the mainframe space, and also get the same process from the web tier, all the way down to the data access tier. And then finally, why do we want to migrate from legacy web applications to microservices? So no one gets up out of bed in the morning and thinks to themselves, I'm going to write an application today and it's going to be an unmaintainable ball of mud. But what tends to happen is over time, the tiers that you put in place people take jumps through them when they shouldn't. The tiers get blurred. So what microservices gives us is a network boundary that enforces a strict bounded context, and all the access needs to go through that network boundary. What this means is that we end up with smaller pieces of code. It's easier to test them. It's easier to deploy them. And it also, over time, once we start taking advantage of those network boundaries, it allows our development teams to adopt other mechanisms for implementation in terms of different languages and also different database storage mechanisms. So rather than just the pure relational that they tend to work with now. Before we started moving to public cloud, we started to implement microservices for use on-prem. Basically, a 7-step process. Each step builds on the capabilities of the last. So we have the monolithic applications on the far left-hand side, all the way to next-gen apps or microservices on the far right. The first step was start to monitor our code, builds, instrumentation, so that we could produce clean modular code. This would enable us to isolate the data layer from the business the business logic. Once we have that data layer isolated, we can start to define bounded contexts, start to split things up into services. And once we define those bounded contexts, the step to cloud, in order to enable the step to cloud, we really needed to make sure that we were completely stateless within our microservices, and that would give us the kind of elasticity that we were looking for. The steps aren't purely technical, there's some cultural ones here. So the move towards being able to be completely agile and take advantage of experimentation was something that our business was very interested in. But moving from a framework that was originally developed for use on an on-prem private cloud environment to a public cloud required some additional thinking. So you see secure up there. I'm not suggesting that we never thought about security until we went to the public cloud, but we had to think of it differently. Because with public cloud, we started to experience the situation where members of staff would suddenly see things in newspapers, right? Some company left their S3 bucket exposed, all their data was leaked, and they end up in the newspapers. We started to have to ensure that instead of going through a process where we would validate the security model and then implement the tool, we would have to be able to continually be able to answer the question, what do we have in place that would prevent that from happening here? So it's just a slightly different way of looking at security. As part of the move to public cloud, we wanted to make sure that we were able to take advantage of multiple geographic regions. So rather than just a single one and all of our customers from all over the world coming to one place, we wanted to be able to move the compute and data out to them, make their experience as good as possible. We also wanted to be autonomous within a single region. So if there was an availability problem, a disaster problem, a networking problem, we wanted them as much as possible to still get that really good user experience by accessing resources as close to them as possible and be able to cope with the fact that we may lose connectivity to other regions. We wanted low latency from two different perspectives. The first perspective would be from the real-time movement of data from customer to us. But the second perspective is from the user's perception of latency. So rather than clicking on a button and seeing the little whirly hourglass for many seconds before something happened, even though we might be transferring the data, allow them to continue with what they wanted to do as quickly as possible. We needed to think about compliance. We always think about compliance, but now the regulators are going to be walking in and saying, we know you're using public cloud. It's potentially a different level of compliance that we need to be able to show, different level of transparency. And then finally, need to be cost optimized. So when you're working with an on-prem environment, everything kind of the costs to the development teams are often completely opaque. They have no idea. It's a lot more obvious when we're looking at cloud. In terms of cost optimization, I heard an interesting analogy. Anybody can build an expensive bridge that doesn't fall down. The trick is to build the cheapest possible bridge that doesn't quite fall down, right? And that's kind of what we're trying to do with cloud. What's the bare minimum that we can get away with while still providing the customer experience that we want? So with all these in mind, we spoke to a number of teams within the organization. We got a set of requirements from them. We came up with designs. We iterated through the designs. We spoke to a number of partners and consultants and said, this is what we're thinking of doing. And we came up with a design that met all the requirements. And before you start adjusting your glasses, it's purposely blurred. It did meet the requirements. It used a hub and spoke model, right? We adopted a hub and spoke model because that way all the updates would happen at a central location. There was no possibility of conflicts, and it meant that we could use our existing business logic to validate what was going on. We're utilizing the cloud for the spokes. So where we wanted to move the compute and data as close to the customers as possible, that would be at the end of the spokes. There was a number of decisions made in the past with respect to the container management system that we incorporated, and also in terms of an object store caching layer. The object store caching layer was originally conceived to reduce the number of transactions that we were running on the mainframe. In order to deal with the fact that we had the relational model on-prem in DB2 and the object model out in the cloud, there was a fairly sophisticated object relational mapping that worked in two different layers. The first, if there was a cache miss in the object store, and the second, when changes were actually happening to DB2 outside of this system, via batch, via our existing monolithic applications, taking those changes and replicating those out to the object store at the spokes. Because this design required making two writes, one to DB2, so that our existing systems worked, and to the object store at the hub. The hub is the bottom blue box. We came up with the concept of business events so that we could get something in that was agnostic to the actual data platform being used, and then could be translated into SQL code for talking to DB2, and API calls for updating the object store. Because we wanted to keep the object store and DB2 in sync, we're using a two-phase commit to achieve that. The solution was asynchronous, so definitely eventual consistency, where when a microservice would make a change, if it immediately read the change from the object store, it would not see that change. We still had a reliance on proprietary hardware, and in fact, we were actually running more code on the mainframe as part of the process to get away from it. And we were leveraging no managed platforms, so still doing an awful lot of heavy lifting ourselves. As we started to become more familiar with public cloud and looking at moving towards public cloud, we started to look at how can we split that hub and move more of the workloads out. We came up with this concept of an extended hub. So the hub would be extended between us and our closest region, US East 1, and the spokes would still be located around the world. Complexity increased. So we decided to take another look. How could we do things differently? We took the list of requirements that we originally had, and rather than try to build the solution to meet those requirements, we said, what is the simplest thing that we can possibly do, and what subset of the requirements do we actually meet with that solution? We actually came up with 9 options. This is option 1. There was actually an option 0 that was just so awful in terms of functionality, I'm not even showing it. But basically, the microservice and batch processes would write to DB2 directly, DB2 being at the very bottom box there. A change data capture process, if you're not familiar with that, it's basically something that reads the database transaction logs and then makes those changes into another database or another system. So the CDC would pick those changes up, move them to the cloud-based part of the extended hub, where they would be written into the 2 databases. Those databases that would then be read by the microservices, and since those databases would be local to those microservices, the user experience would be good for read operations, which is 90+% of our actual traffic. The system is considerably easier because, or considerably simpler, because there is no need for a translation between a relational and an object model with this particular design. We're moving from relational to relational. The CDC handles it. It makes life nice and simple. And it's fairly easy when you're working with one RDS database to get easy improvements with scalability by adding read replicas and availability by going multi-AZ. Option 3 implemented more of the requirements that we originally had. So one of the problems with option 1 is that if there was a network problem between the microservices and the DB2 database on-prem, effectively the microservice is waiting until the timeout occurs. Users who are trying to make an operation involving a write are waiting for the little hourglass to finish. With the buffered writes option, the microservice writes to a streaming data platform located in the same geographic region. It uses the business event when it actually writes that message, and the business event is propagated down to the extended hub, which makes the write to the DB2 database. The user perceived latency as a result is very low. The availability and disaster impact is considerably lower because our users can still make writes to the database and they're stored before they're forwarded. And if we have an incredible increase in traffic, the part of this solution which can't scale is the database at the very bottom on the mainframe, and we can absorb the spikes using the streaming data platforms. A couple of the requirements that we had, though, were the single integration point. What we wanted to give our SI organizations was, instead of having the need to write integration across multiple point-to-point solutions, they could go to a single place to see what was happening with the system. And asynchronous writes were still a fact of life. Eventual consistency was still a fact of life. The idea there was that it would be solved in the application layer, talking to the microservice. I'm going to go into a little more detail about the buffered writes, how we achieved it. So what we wanted was that because we had this asynchronous system, that applications would be aware of where they were when asynchronous writes were happening. So the microservice would write to the streaming data platform. A piece of code there, labeled the replicator, would take that, move it down to on-prem, where it would be picked up by a dispatcher. The dispatcher would then look at the business event and determine which microservice can actually make this update in our DB2 database, and it would make the appropriate call. The reason for the double hop there is that the microservice teams that own the bounded context could implement the Lambda functions and deploy those independently in order to have control over their own data and make the updates in the database that made sense to them. In the event of everything working correctly, the dispatcher would get back a good return result. It would append some information to the business event that we could use for analytics, for example, the processing time, and it would then push the business event into the done stream, and that would be propagated around the network. By using the IDs in the to-do and the done stream, we can then determine that a particular operation has happened. And in the event of an error, the message would end up in the error stream, so everyone would be aware by looking at the error stream that there was a problem that occurred. We developed a microservice that would actually read from those various streams. So the bounded context for the Kitty Hawk microservice was actually the logged in user. So an application which didn't necessarily need to know about every microservice it needed to deal with could still determine if there were things in flight that might impact its operation. And we called that microservice Kitty Hawk because it deals with in-flight messages during write operations. So continuing along the various different options that we offered the lines of business. We were aware that some of the lines of business were very interested in not sticking with a relational model, but instead looking at a NoSQL option. So we came up with this solution. Uses a NoSQL data store. I'll walk you through. Basically, when a write happens to DB2, the CDC tool, again, picks up the transaction, moves that into the hub, where the CDC tool then takes that transaction data. Instead of writing it directly to a relational database, it puts it again into a streaming data platform. The message is then read from the streaming data platform, and then based on the contents, the tables, the rows that are actually impacted by that change, it calls another, what we call event writer. And then the event writer pushes the message through to the same streaming data platform on the left-hand side that was used by the write process. The dispatcher then picks it up, passes it to the DB writer. Because of identifiers that the event writers put into the message, we can determine that that message came through the CDC process. So rather than update DB2, we update the NoSQL platform. We now have our single point of integration because all changes to the system are flowing through the streaming data platform on the left-hand side. So anyone can write code at that point of time that looks at that streaming data platform and is able to determine all the changes that are happening to the system. We have our relational to NoSQL mapping happening in the event writers and the DB writers spread across those two components. We're able to leverage a NoSQL data store. We have a slightly higher latency, but it's somewhat hidden from the user. But we have introduced significant complexity. But we've given it to our users as an option, right? Do you want option 1, simple? Do you want option 6, more complex? And the users were able to look at the requirements that were implemented with each approach and make the decision for themselves rather than take a one-size-fits-all. So what did they actually pick? Lines of business couldn't decide. One line of business still wanted to stick with relational. The other line of business wanted to move towards DynamoDB. It's really interesting being here this week. We've seen significant announcements about both, right? Aurora for Postgres, now available serverless, for example. Global tables for DynamoDB, now available. The solution then gives us both. In addition, because we are taking the data, replicating it from on-prem out into the cloud, the analytics part of the organization also said we could leverage that. If you're pushing the data out through the CDC tool, we can siphon it off, use that as well for big data analytics. So that's been added as well. What we have now then is a system where if there's an availability event, a microservice that's based out on one of the spokes can still read everything that it needs to from the databases. We'll have an idea when we replicate the data out exactly how stale that data is. When the user wants to make an update, the update is moved into the streaming data platform. Even if we can't replicate that data down to the hub, at least it's there. We can let the user off the hook. We understand their intent. And then all the work still goes on in the hub, and we're reducing our on-prem footprint. Sorry, just to go through, the green lines represent the relational process, and the purple lines represent the NoSQL process that you saw on the last slide. So in terms of mainframe strangulation strategy, what we've seen here is like the first step. We take the data, we move it out into the cloud. We've provided ourselves with an abstraction layer where the microservices can be built to interact with the data format that makes the most sense for them, either relational or NoSQL. They can be deployed. They don't need to know about all the rest of the process that keeps those data stores up to date. We then start to take our monolithic applications. So at the moment, those monolithic applications are used to making calls to the database, getting the data, building the HTML code, sending effectively the page all ready to be rendered back to the browser. We need to take that and remove some of that rendering so that what we actually send back to the browser now is the instructions that said, once you get this page, you need to go back to the microservice, grab the data that you need, and render the page yourself. So basically refactor the monolithic apps, make AJAX calls to the microservice, grab the data, and display it as necessary. In parallel with that, migrate batch processes to the cloud so that the data that is in the cloud now that we've replicated out there is used for the batch process instead of DB2 on-prem used for the batch process. We're looking at the kinds of batch processes that we have that operate within a single bounded context. Once we start to move batch process out to the cloud, and some of those will require orchestration type services that work across multiple microservices in order to perform those types of operation. But once we're able to move those batch processes out to the cloud and we're at the stage where a particular bounded context is no longer accessed within our on-prem database, then we can start to switch the replication so that we keep the gold copy of the data in the cloud and we push the data back down to DB2 should it be necessary to actually read it there. But everything's actually happening in the cloud. For the short term, we're keeping the mainframe record-keeping systems, the CICS, the vSAM, the COBOL systems, treating those as bounded context. So the integration logic that we had that would take the data from DB2, move it into vSAM at the beginning of the batch process, and then at the end of the batch process would take that data from from vSAM and move it back out to DB2 at the end of the batch process, would instead, at the beginning of the batch process, move the data from the cloud into vSAM, and then at the end of the process, from the vSAM files back out into the cloud. And obviously, over time, chip away at this process, move as much as we possibly can out into the cloud, and basically strangle what we're doing. So there's a few different Amazon services that we use in order to accomplish this. Relational database service. Basically, what we looked for when we were working with any Amazon service is four things. First of all, SOC 2 compliance. So many of our applications need to be SOC 2 compliant. Our customers are looking for that in the institutional space. Next thing is data at rest encryption. So mandate came down from security that every piece of data that we store in Amazon needs to be encrypted at rest. User access management is basically where we are absolutely sure about which users exist within our various data stores and the rights that those users have. And the ability that if someone leaves the company, we can be absolutely sure that within minutes, their rights are removed from those databases. And then finally, data activity monitoring is the recording of every select, insert, update, and delete that happens on those databases, which is absolutely necessary for consistency, integrity, and also data loss prevention, right? We can tell exactly when data was read from our database. So with RDS, we were really lucky that SOC 2 compliance came straight out of the box, and data at rest encryption has been available for years. User access management was more difficult. The on-prem systems that we had for accessing databases did not work with the database that we were looking to target in Amazon, so we ended up writing a REST interface that would integrate with our on-prem IDM system and create and delete the necessary user IDs and roles from the RDS databases. It also offered the capability that we can, on demand, request a list of all the users and all their roles and all their accesses in a database that we can give to auditors in order to prove that we're meeting that particular requirement. Data activity monitoring. We use a third-party product on-prem that tracks all the select, inserts, updates, and deletes to DB2. It could not be used with RDS because it requires installing an agent on the actual box. We're able to get around that particular issue by pulling the RDS logs every so often from RDS, moving those into a log consolidation system, and monitoring for particular access. So we could actually see what was going on there. DynamoDB, again, lucky it was SOC 2 compliance. There's no data at rest encryption for DynamoDB. So we're taking advantage of client-side encryption there. You're basically encrypting the data before we move it to DynamoDB. That certainly imposes some restrictions on what we can use DynamoDB for. You suddenly lose the ability to filter or query on the data that you've encrypted. User access management for DynamoDB was fairly easy to achieve because it's tightly integrated with Amazon's IAM, Identity and Access Management Service, so that was easy to achieve. And data activity monitoring was also something that was missing. So DynamoDB streams gave us the ability to monitor updates, deletes, and inserts to the data, but we couldn't monitor the selects. So potentially there's a data loss issue there. We solved this by, again, using client-side encryption, and then taking advantage of the fact that we do get a log of CloudTrail access to KMS. So every time someone actually grabs the key in order to decrypt the data, we do have a record of that. For AWS Lambda, 2 or 3 weeks ago, was it? SOC 2 compliance was granted for AWS Lambda. Up to that point, we were very careful about our app selection, and also AWS engagement constantly talking to the SA Ilya saying, when are you going to be SOC 2 compliant for Lambda? Data at rest encryption is not really an issue. User access management, again, because it's integrated with AWS IAM, and data activity monitoring, not an issue for Lambda. Amazon Kinesis is also part of the solution. SOC 2 compliance, again, was granted a couple of weeks back in exactly the same way. Up until that point, it was being very careful about the applications that were selected and constantly asking AWS, is this going to be available? It's really important to us. Data at rest encryption was announced back in July, so we were really happy about that. It stops us jumping through hoops from the encryption perspective. User access management, again, is provided by AWS IAM. And data activity monitoring is not available for certain types of data that need it, we can use client-side encryption, and again, we get the KMS and CloudTrail logs when we decrypt that data. So what are the impacts of migration? So firstly, the unmaintainable big ball of mud is gone with the microservices, right? We can use CD pipelines, we can pull the data, we use the pull request model to force a peer review. So whenever our users are making changes, someone else has to approve those changes before the actual code moves from their particular feature branch into the main branch. It gives us some quality controls, and as a result, we're doing continuous builds of this, improving quality and code coverage of tests. Microservice principles, we have the strictly enforced bounded contexts, and the move on the NGA stack to cloud means that we have stateless and therefore much more highly scalable services. The negative of the microservices approach as opposed to the on-prem is the eventual consistency, which we're solving using at the application layer and the Kitty Hawk microservice. From a cloud perspective, we have our infrastructure as code pipeline. So basically, we're making extensive use of CloudFormation in order to set up these environments that we're using. In the same way that our code goes through the peer review pull request process, so does our infrastructure. We have the same kind of quality gates and rapid feedback when we're standing up infrastructure now. Making extensive use of managed services in the public cloud, so DynamoDB, Amazon RDS, Kinesis, Lambda. There's a lot less heavy lifting for us to do. But of course, by moving to the cloud model, we are now dealing with eventual consistency and latency. Again, solved at the application layer. And finally, with this approach, we've moved and achieved the requirement for a single development model. Developers are no longer needing to write COBOL code to run on the mainframe. They're now writing Lambda functions that can reach through, pull the data out of the mainframe. The direction we're giving them is try to use frameworks that even make that agnostic so that we can continue to start taking advantage of new technologies, right? If you're talking to an RDS database today, think about what it would take to actually move to NoSQL in the future or whatever comes next. We've achieved the goal of polyglot in terms of data stores and languages. So by having the network interface between the various components of the system, we can implement a microservice using almost any language as long as the interface remains the same. The caller, the client of that interface, doesn't even need to know the language that it's developed in. So that's a huge change from the monolithic code base. And also in terms of data stores. So we're now able to tell our developers, if your particular microservice makes, for example, extensive use of relationships, then maybe a graph database is the right thing for you to use rather than relational, rather than NoSQL. It gives us that kind of flexibility. And I've got compliance on there as a bullet point. In some respects, compliance is easier. We have the compliance information from Amazon, so we're effectively leveraging their compliance rather than having to do everything ourselves. But there's certainly an increase in scrutiny. So lessons learned basically fall into three separate categories. From a regulatory perspective, when you're working with a large monolithic database, it's very easy to see everything within that database as being sensitive, PII type data. When you're taking that database, splitting it up into multiple different bounded contexts, moving it around to different microservices, it's possible to think of it differently. So understanding the different data classifications is really critical. Being able to treat those different data classifications in different ways for different microservices can save you a lot of time and effort in terms of the possible solutions that you can use. We've often found that it's useful to have a backup plan because the particular technology that you most want to use perhaps isn't released when you would like it to be, isn't compliant as you would want it to be, so being able to have another option. And often we've found that self-managed solutions are the answer there. So although a particular managed service may not have the capability that we need, we can stand up EC2 instances and install our own software to use for the short term. In terms of acceptance, so I said earlier, we're not just doing one migration, we're doing 3 migrations, right? And people don't like change. So working with large groups of people, letting them know what's going on, making them part of the process, definitely very valuable. What we found is that work with large teams to publicize, but work with smaller teams to gain consensus and understanding and move forward. And in terms of cloud specific, we've found a number of times AWS has released new capabilities, sometimes just after we implemented something that provided the same thing. But obviously we want to take advantage of the managed capabilities as much as possible. It meant some re-architecture. We've actually coined within the cloud construction team the idea of continuous architecture. So we've got continuous integration, continuous deployment. Now there's continuous architecture. Expect it to change, and then you won't be disappointed. And also build a good relationship with the AWS team. So that's been invaluable for us. We've found that sometimes you go to AWS, if you say, what's your roadmap for the next 3 years, you'll be met with stony silence. They won't give anything away. If you go to them and say, I have this specific problem, I need this, can you help me? We've heard much better responses from, you're not the only person to ask for this, we'll put you on the list, we'll see what we can do to prioritize it, all the way to, hey, we've just rolled this out as beta test, we'll add you to the beta, you can start playing with it right away. So that's it from me. Thank you very much for attending. Ilya and I will be down here to answer any questions. And I know all the swag is probably gone, but if you could fill out your comment cards, that would be greatly appreciated. Thank you very much.